Here we will see the standard electrode potentials of alkaline earth metals, but the standard electrode potential is lower than our alkali metals, but still they are good reducing agents. You remember lithium is minus 3.04, and it is in negative terms it is higher than lithium, meaning it is a weaker reducing agent. Higher the negative reduction potential or negative standard electrode potential, better the reducing agent element will be. So in that we see barium will be the best reducing agent among all the alkaline earth metals. Although beryllium having a low standard electrode potential, but still it's a reducing agent. Just like alkali metals, alkaline earth metals give deep blue-black color solution. Similarly, the reason is formation of ammoniated electrons and formation of ammonia complex of metal atoms. Other is group 2 metal are amphoteric in nature, which means let's say beryllium hydroxide, we add hydroxide in that, we are getting berylliate ion. If we add HCl in that, we are getting BeOH4Cl2. So our beryllium hydroxide reacts with both hydroxides and chlorides. Other element oxides in the group are basic in nature. The covalent character of this group compound decreases and ionic character increases down the group as per FAJAN'S rule. We know smaller the size of cation, larger the size of anion, more will be the covalent character. But otherwise, if the cation size is large, ionic character will increase. We know now from the FAJAN'S rule, there is no pure covalent character or a purely ionic character do exist for these alkaline earth metals or alkali metal salts. Applying the FAJAN'S rule, qualitatively we can say which side it having a certain covalent character or not. Here is the FAJAN'S rule. Polarizing power of a cation increases with increase in its charge. Smaller the size of a cation, larger the size of an anion, greater will be the covalent character of ionic bond. Here you see, as the polarizability of an anion increases with increase in size of anion. For the same cation, with increase in the anion size, our covalent character increases. In vapor phase, beryllium chloride forms chlorobitch dimer. At a high temperature, 1200 Kelvin, these dimers, breaks up to give us a single monomeric unit. Hydrated chlorides, bromide and iodides of calcium, strontium and barium are dehydrated on heating, like calcium chloride, hexa water molecule. You heat it up, we're getting calcium chloride. Same thing, it breaks up to give strontium chloride, barium dichloride, it is a dihydrate. So these three compounds, calcium, strontium and barium, dehydrates on heating. But first to magnesium chloride, what happens? It is a hexahydrate. You heat it. What happens? First we are getting magnesium dichloride, dihydrate. Upon further heating, it gives you magnesium hydroxychloride. On further heating, it gives you MgO, HCl goes out. So we are getting finally oxides. This is a case of magnesium. In case of strontium, calcium and barium, we are getting pure dichloride salts and water molecule goes out. Here, magnesium salts breaks up to first MgOHCl, then into magnesium oxide. Now, so let's talk about the solubilities. Fluorides are less soluble than chlorides for barium. This beryllium fluoride is less soluble. The reason is here the covalent factor will be higher for chloride compared to fluoride according to FAJAN'S rule. Here you see. So similarly here, magnesium chloride, its crystal lattice will be weaker than magnesium dichloride. On heating, it crystals breaks up easily, and the hydration energy that solubilize will be better for chloride compared to fluoride. So the combination of lower the crystal enthalpy and relatively higher hydration enthalpy release on hydration helps for higher solubility of chlorides. Same thing goes to calcium fluoride and calcium chloride. Here, according to FAJAN'S rule, calcium chloride should have better covalent character, which means its lattice enthalpy will be lower, and the hydration enthalpy in that case, because calcium cation is same, compensate the lower lattice enthalpy, results in better solubility. Here, beryllium carbonate again is having low solubility. But if we look at the solubility of alkaline earth metal carbonate decreases and thermal stability increases with increase in atomic number of elements because of increase in cation size. Here we will see the solubility of it will reduces down the group, but thermal stability is higher. So what we will see, thermal stability of a barium carbonate will be higher than beryllium carbonate. If you remember, like lithium carbonate decomposes to give us lithium oxide, same thing goes to the beryllium as well. For the same reason, the smaller size having a larger charge to radius ratio, which improves or helps us to stabilize the oxo anions. Now, carbonate of alkaline earth metals insoluble in water can be precipitated by the addition of sodium or ammonium carbonate to a solution, this is what happens. Sodium carbonates having a better solubility than these alkaline earth metal carbonates, so they replace them and these carbonates will come out. Because of, if you remember, this all happens because of the Chatelier's principle again. It increases the carbonate concentration in that solution. To compensate it, this alkaline earth metals carbonates precipitate out. Solubilities of alkaline earth metals sulfate decreases with increase in the atomic number. The greater hydration enthalpies of beryllium and magnesium and overcome the lattice enthalpy factor. That's why beryllium and magnesium sulfates having a better solubilities compared to lower alkaline earth metal sulfates. Here we are having a magnesium nitrate, hexahydrate. What happens? The group 2 elements, their tendency to form nitrate increases with increase in size and decrease in hydration enthalpy. So down the group, they forms nitrate compounds. Now let's briefly look at the comparison of solubility of alkali and alkaline earth metal compounds. First, sulfate solubilities. Alkali metal sulfates are highly soluble and they form alum very easily. Alkaline earth metal sulfates are sparingly soluble compared to alkali metals. Next is solubility of bicarbonates. Alkali metal bicarbonates are less soluble than their corresponding carbonates, but bicarbonates of alkaline earth metals are more soluble than the carbonates. So it is the reverse for alkaline earth metals. Now, fluorides, carbonate, phosphates and oxalates. Fluoride, carbonate, phosphates and oxalates of alkali metals are more soluble. Alkaline earth metals are less soluble, that you remember. Now, one important construction material from alkaline earth metals, calcium sulfate dihydrate, also known as gypsum. Plaster of Paris is produced by heating a gypsum at 150 degrees Celsius. 1.5 molecule of dehydrated water loses. We will be left with calcium sulfate, half hydrated water, which is used for different materials. Now let's try to look at certain biological applications of calcium and magnesium. Many of enzymes, which are a biological catalyst, utilizes ATP in the phosphate transfer. They require magnesium as a cofactor. Cofactor means it's an aid in enzyme. Here is the magnesium. We know the life on Earth is due to one plant activity known as photosynthesis. And for the photosynthesis, plants require one particular pigment for the absorption of light known as chlorophyll. The activity of chlorophyll is because of alkaline earth metal magnesium. So we can say without magnesium there would have been no photosynthesis, and without photosynthesis there would have been no life on earth. So it reflects how important these alkaline earth metals are for biological life. You see, this is how chlorophyll looks like. Here is a magnesium atom at center. This is an organic molecule of chlorophyll. In our body, 99% of the calcium is present either in bones, teeth, and it having a very important role in nerve signals, neuromuscular functions. Here is a motor neuron, skeletal muscle fibers. So this information from our neurons to these muscles happen through calcium plays an important role in that. Here is an example of a neuron. Neuron nucleus, neuron cell body, and these are all dendrites through which these are tentacles through which these signals flow. One of it is called axon. This is axon terminal. In case of bleeds, there is an important activity called coagulation. For this coagulation, calcium is one important factor. Fibrogen. Beryllium, you see, because of its small size, low density, and got very low X-ray attenuation. Attenuation means reduction in intensity. For this reason, metallic beryllium is used for making windows for X-ray tubes, because it will not reduce the intensity of X-ray required. Other applications we can see. Magnesium aluminum alloys called magnesium, being lightweight, their uses for these aircraft bodies. And many high-end automobiles also have use of magnesium aluminum alloys. Beryllium copper alloys, because of their strength, using for high performance tools. Because of lightweight, magnesium alloys allow to reduce weight in automobiles without having any compromise on strength. So we see these magnesium alloys used in many defense applications, automobiles.